All right, let's take a look at the PowerPoints for Chapter 5, Regression. In Chapter 5, we cover regression lines, the least squares regression line, using technology, facts about least squares regression, residuals, influential observations, cautions about correlation and regression, and the fact that association does not imply causation. A regression line is a straight line that describes how a response variable, y, changes as an explanatory variable, x, changes. We often use a regression line to predict the value of y for a given value of x when we believe the relationship between y and x is linear. Example, predict the gain in fat in kilograms based on the change in non-exercise activity, NEA, change in calories. So first we make a scatter plot of the data with the x-axis being the change in NEA and the y-axis being the gain in fat in kilograms. So we're predicting the fat gain, so that's a y value, from the change in non-exercise activity, that's an x value. We're going to answer the question, if the NEA change is 400 calories, what is the expected fat gain? The regression line describes the overall pattern of the relationship that we see here. Review of a straight line. So suppose that y is a response variable plotted on the vertical axis and x is an explanatory variable plotted on the horizontal axis. A straight line relating y to x has an equation of the form y equals a plus bx. In this equation, b is the slope, the amount by which y changes when x increases by 1 unit. The number a is the intercept, the value of y when x equals 0. To plot the line on the scatter plot, use the equation to find the predicted y for two values of x, one near each end of the range of x in the data. Plot a line each y above its x value and draw the line through the 2 points. Least squares regression line. The least squares regression line of y on x is the line that makes the sum of the squares of the vertical distances of the data points from the line as small as possible. Equation of least squares regression line. We have data on an explanatory variable x and a response variable y for n individuals. From the data, calculate the mean x bar and the mean y bar and the standard deviations s of x and y sub x of the two variables and their correlation r. The least squares regression line is the line y hat equals a plus bx with slope b, which equals our correlation r times the ratio of the standard deviation of y over the standard deviation of x. So the change in y over the change in x. And the intercept is a, which equals the y average, so y bar minus b times the x average, or x bar. Prediction via regression line. For the non-exercise activity example, the least squares regression line is y hat equals 3.5051 minus 0.0034x. Y hat is the predicted fat gain in kilograms with X calories of non-exercise activity. Suppose we know someone has an increase of 400 calories of NEA. What would we predict for fat gain? For someone with 400 calories of NEA, we would predict fat gain of 3.5051 minus 0.0034 times 400, which is 2.1451 kilograms. If we look at the visual from the beginning, we see that at the 400, if we follow it to the red line, that has a value of about 2.15. Using technology, we can do the calculator, right? The mini tab, Crunch It, which is the app. I don't know if it works. And then the Excel. So you can see that the output from the calculator is y equals a plus bx. A is listed as 3.5051. B is negative 0.0034. Again, on the mini tab, for constant, under the coefficient for the constant, we see the 3.5051, and the coefficient for the NEA is negative 0.0034. So you can see the output on each one of these. On the Crunch It, it's under the estimate column, and on the Excel, our output is in the B column under the header coefficients. Facts about least squares regression. The distinction between explanatory and response variables is essential in regression. There is a close connection between correlation and the slope of the least squares line in. The slope is B equals R times the standard deviation of y divided by the standard deviation of x. The slope b and the correlation r always have the same sign. Along the regression line, the change of one standard deviation in x corresponds to the change of r standard deviations in y. The least squares regression line always passes through x bar, y bar, the point x bar, y bar, on the graph of y against x. That's the point of the means. The square of the correlation, r squared, is the fraction of the variation in the values of y that is explained by the least squares regression of y on x. Residuals. Residuals represent leftover variation in the response after fitting the regression line. Residuals are the difference between the observed value of the response variable and the value predicted by the regression line. That is, a residual is the prediction error that remains after we have chosen the regression line. So residual equals the observed y minus the predicted y. So the y that we're given as data minus the y that the least squares line itself predicts as the value for y. The residual from the least squares line have a special property. The mean of the least squares residual is always 0. Residual plots. A residual plot is a scatter plot of the regression residuals against the explanatory variable. Residual plots help us assess how well a regression line fits the data. Look for a random scatter around 0, the residual plot. So here we have empathy on the x-axis and brain activity on the y-axis. This is a scatter plot of the data with the least squares line. And if we plot the residuals, then the X values are still the same. And what we're plotting is the difference between the first graph's blue dots and the red line. Influential observations. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. The result of a statistical calculation may be of little practical use if it depends strongly on a few influential observations. Points that are outliers in either the X or the Y direction of a scatter plot are often influential for the correlation. Points that are outliers in the X direction are often influential for the least squares regression line. So here we have the empathy score and brain activity. From all the data, R squared equals 51.5%. After removing the observation, the 16th observation, our line is shifted, our least squares line is shifted, and R squared is 33.1%. So correlation and regression lines describe only linear relationships. Correlation and least squares regression lines are not resistant. So we saw removing one entry pulled the line to a different location. Beware of ecological correlation or correlation based on averages rather than individuals. Beware of extrapolation, predicting outside of the range of X. Beware of lurking variables. These have an important effect on the relationship among the variable in a study but are not included in the study. So beware of extrapolation. Sarah's height was plotted against her age. Can you predict her age at 42 months? Yes, because it's in the range of data, right? We plot our least squares regression line and we find her age at 42 months. Can you predict her height at 30 years, 360 months? Not likely, right? Because according to the best fit line of the data we were given, her height is estimated to be 209.8 centimeters. So she's predicted to be 6'10" and a half at age 30. So unlikely. So extrapolating is trying to make predictions on values, X values that aren't part of your data set or aren't in the range. So another caution is to beware of lurking variables. So meditation and aging. We have the explanatory variable is observed meditation practice, yes or no question. And the response variable is the level of age-related age-related enzyme. General concern for one's well-being may also be affecting the response and the decision to try meditation. So you can't necessarily say that because you do see a correlation that there's any causation, right? So you can't say they have actually anything to do with each other. It may be something else that's making both of these rise or making you see what you think you see. It's a hidden variable you aren't considering. Correlation does not imply causation. Even very strong correlations may not correspond to the real causal relationship. Changes in X actually causing changes in Y. So correlation may be explained by a lurking variable, social relationships and health. Does lack of social relationship cause people to become ill? There was a strong correlation. Or are unhealthy people less likely to establish and maintain social relationships, reversed relationship, or is there some other factor that predisposes people both to have lower social activity and become ill? Evidence of causation. A properly conducted experiment may establish causation. Other considerations: when we cannot do an experiment, the association is strong, the association is consistent, higher doses are associated with stronger responses, alleged cause precedes the effect in time, alleged cause is plausible, it is a reasonable explanation.